So today I wanted to take an interesting approach to deriving the wave equation because most derivations, including the one I did within my class, involved an assumed solution, which is kind of like a circular definition. So I thought it'd be an interesting thing to try to derive it mathematically, and here I think I found an interesting property that leads to a direct derivation. So let's consider the Laplacian as just the sum of all second derivatives with respect to all spatial coordinates of a coordinate system. Let's consider a coordinate switch from standard Cartesian coordinates to space-time coordinates, but I'm going to make a slight alteration. So we're just going to let x equal x, of course, but we're then going to let y equal ct such that it satisfies the invariant. So it will be x squared minus c squared t squared is invariant. If it wasn't I, then it would be just plus, and then it wouldn't satisfy the invariant. So considering the chain rule, the multivariable chain rule, we have df, oh my pen's dying, one moment. Okay, we're back with a new pen, a red pen. So we have df dx is equal to df dx dx dx, which seems counterintuitive, but we're simply writing that because we let x equal x, plus df dt dt dx. So that's the full multivariable chain rule for this coordinate. This is just df dx because dx dx is 1, but dt dx is 0 because there's no x within the t term. So this goes off to 0 and we're left with df dx. So we're essentially saying here that the second derivative of the function with respect to space is equal to the second derivative of the function with respect to space, which no-brainer, right? Sorry about my shitty facial hair. I look homeless. Yeah, so we'll consider the same for the time coordinate. So we'll have df dy is equal to df dx dx dy, which will go to 0. Then we have df dt dt dy. dt dy, if we get t divided through by c, we get I y over c. So dt dy is going to be just I over c. So df dy is going to be equal to I over c df dt. So the second order term is going to be d2f dy squared is equal to I squared over c squared times df d squared f dt squared, which will be minus 1 over c squared d squared f dt squared. And then to get an expression for the Laplacian, we simply add them together. So then we get the Laplacian, can you see this? Yep, d squared f equals d squared f dx squared minus, this is hard, d2 squared 1 over c squared. And that's the wave equation if we set that equal to 0. So the spatial gradient of a wave is equal to 0, and that's what leads to the wave equation. It's simply the Laplacian in space-time coordinates. Quite interesting here. I think this also says something a little bit more about the nature of waves and says something a bit about their fundamental nature in reality. Because any function that satisfies this equal to 0 is defined as a wave within the wave equation, given that this is simply the Laplacian in space-time coordinates, it seems very much like that shows just how fundamental a wave actually is, if that's all it is, right? When we derive the wave equation, typically it doesn't seem to be as normal as this makes it seem. So I think it's just quite interesting.